Good morning, all students. As I am audible for you, screen is visible for you. Yeah, okay. So, last time we have started about the basic theory about the PN junction diode. Now, we will take it slightly review of the previous lectures and then we will start the presentation one by one of our next further points. Yes, lastly, we have seen that the PN junction diode. Yeah, we know that what is a PN junction diode? If one half of a is doped by P region and another half of a is doped by N region impurity, then PN junction diode is formed. So this is called as a PN junction diode. So finally, in the P type P side, we will have the majority carriers as holes and the minority carriers as electrons. In the N side or N type, we have majority carriers are the electrons and the minority carriers are the holes are there. So what we'll have, if you observe that for a P type and the N type, there is having a concentration of carriers. In the P side, we have the whole concentration, and in the N side, we have electron concentrations are there. Now what will be there? These holes from the P side material and the electrons from the N side material. So electrons from the N-side materials try to cross this junction, or they have a tendency to cross the junction. So once they are crossing the junction, the free electrons from this one, it will be combined with the holes, and there will be a recombination between electrons, and the holes will be takes place, and they will be a disappear or a diffuse. So therefore there will be have a diffusion process is takes place near the junction. As the diffusion process takes place, so as a electrons is entering to the crossing the junction and entering into the P region. So they will be behave as a dopant or a donor, and so they will be as it is behave as a donor, they will be create a positive ions near the junction. Similarly, at the N side, P side, where holes are combining with the electrons, they are accepting the free electrons. So they are acceptor, and as they are acceptor, they create a carrier, negative carriers or negative ions near the junction. So this is the one of the combination I have explained for one combination. So similarly here number of combinations are takes place. So the number of ions are to be found near the junction. For a P side, the positive ions are accumulated, and the N side, sorry, for N side, positive ions are accumulated, and for a P side, negative ions are accumulated. As here these ions are accumulated, okay, as ions are accumulated, also we have seen that here majority carriers are the holes and the minority carriers are the electrons, whereas for the N region majority carriers are the electrons and the minority carriers are holes. So they have their concentration gradient, which is represented by like this way. So here for the P region we have the electrons concentration gradient is a more, and whereas for the P region we have the holes are majority carriers and their concentration is large, so which is represented by a dotted line. So this is the holes and the electron concentration. So means if you observe that here these electrons are moved from N region to the P region, yes, and the holes from the P regions are moved from P region to the N region. So electrons will be from right to left, yes, and the holes will be from left to right. This will be a combination between. So means here majority combinations will be takes place and the minority carriers are will be also there. Now what will be happen once this barrier potential is developed? Sorry, this barrier is developed. Then barrier is developed near the junction. Here are positive ions in N sides and the negative ions in P sides. They will be generate the electric field, or they will be generate a potential, or it will be called as electrostatic force. So as it is generate electrostatic force, this terminal will behave as a negative terminal and this terminal will be behave as a positive, and so therefore there will be a we have the electrostatic force or electric field is developed across the junction, and this electrostatic force or field is developed is called as a barrier potential. And so as a, since it is a barrier potential is developed, they will have the they will be create the space near to the junction, and so it's also called as a space charge region is also there. So this will be have the barrier potential. Now what will be happen once this barrier potential is generated? Then whatever the electrons are there, majorities and the minorities, majority carriers and the minority carriers from the N side, and majority carriers and the minority carriers from the P side. Before this recombination to be takes place, there is a sorry, before this deflection layer is formed, there will be recombination between electrons and the holes is going on. But once this barrier is developed, potential deflection layer is developed, then the recombination between electrons and the holes, electrons are not try to move, not trying, electrons are not unable to move from the P region to the N region, or holes not will be combined with from P region to N region. So definitely means what? Once the barrier is developed, there is no movement of carriers. As there is no movement of carriers, there will be a no movement of sorry, there will be a no flow of current. Yes. So means it can be said that here. So here before a recombination, before a deflection layer, recombination takes place, and once the deflection layer is formed, recombination does not take place, guys. So means what? That this uh, can be represented as the electric field potential will be slowly developed according to this. So lastly, we have discussed about this one, and we have found out this barrier potential, contact potential at the junction. If no voltage is applied externally to the PN junction diode, and which is given as a V subscript T logarithmic log to the base E of a acceptor and the donor concentration divided by intrinsic constants will be there for intrinsic constants, and based on that one last slide we have so numerical based on this one. So we will continue with the discussion that if we consider that diode is a forward bias, when the diode is a forward bias, when positive terminal of a battery, external battery, is connected to the P side, and the negative terminal of a battery is connected to the N side, then that combination is called as a forward bias. So since it is a forward bias, this positive terminal, yes, what will have? This positive terminals will be emit its ions, negative terminal which will its emits the ions, yes. So therefore these negative ions will be combined with these positive ions, okay. So as there is a number of positive ions and the negative ions near to the junction, if we concentrate for N side, the negative ions from the battery will be combined with positive ions in the N region. So therefore here, guys, we have here. Here number of layers we have here. One more can be a recombination. Okay. Here, if we consider that before applying external volt, one more one more line is present, one more line offered in the deflection layer which is have positive ions, and similarly for a p side one more column will be there negative ions. So this is a before applying external force. If we apply the external force, these negative ions will be combined with this additional, yeah, positive ions, and once they will be combined, they will be disappear. So once they will be disappear, one of the, so few of the recombination will be, few of the recombinations does not take place. So finally, this width was, which was a more in the no bias position, which will goes to the reduce. Similarly, for the p side, the positive ions from the battery will be combined with here negative ions at the near the junctions. They will be combined. Recombination will be take place. As the recombination takes place, they will be disappear. Once they disappear, they will be reduced the accumulation of their positive negative ions near to the junction. So we can say that here for the forward bias configuration, this deflection width, which was quite wide, that will goes to the reduce. Yes, in case of a forward bias region. Now what will be there as here? If you see that for this, once the barrier potential is developed, there will recombination will never takes place. But so means we want here as a recombination, barrier potential is reduced, barrier layer is reduced. So therefore definitely this barrier potential is also reduced. So if we apply here external force, let V amount will be there such that it will be more than the barrier potential, then this barrier layer or barrier deflection layer will be destroyed or it will be a break. Once it is a barrier layer will be a break, they will be disappear. And so since they disappear, then these holes will be combined with the electrons or these electrons will be moved to the holes. So finally the current will be, finally there will be a movement of majority carriers from a p side to the n side and electrons carriers from n side to the p side, and thus we know that finally the current will be flowed through a forward bias configuration. So according to that concept, it we have the characteristic voltage versus the current. So before, so if we apply external voltage here, before barrier potential, yes, this barrier is exist, and so therefore no recombination, no movement of electrons and the holes, no flow of a current till the it's a barrier. So it's a till the it's a barrier potential. Maybe for germanium it will be 0.3 and for silicon it will be 0.7. So once your applied potential is greater than this potential, barrier potential, so let's, if we consider a germanium material, for that case, barrier potential is a zero point 0.3. For that scenario, if external voltage is greater than this germanium potential, germanium breakdown voltage, germanium barrier potential, then this barrier will be disappear and the current will be flows, and so the current will be released linearly. Similarly, if we consider that this material is made up of with silicon material, for that scenario, it's a barrier potential is a zero point 0.7. So before a zero point 0.7, there is no movement of electrons, no current flow, but small amount of a current is starts flowing. And then once barrier potential is a break for a silicon 0.7, then current will be immediately raised. Now what will happen for the reverse bias? Under the reverse bias when positive terminal of a battery is connected to the P side and the negative terminal of a battery is connected to the N side. Before applying external potential, we have here a barrier. Yes. Now if we connect the battery, this battery will be emits negative ions as well as a positive ions. So from a positive terminal battery, it's a positive ions are here. Okay, it will be a accumulate here, it will be a enter into the p region, and so there is a positives are there. There is a no recombination takes place, so they will be accumulate near the junction. Similarly, what will happen at the n side, p side? From the p from a p in the p region, from a negative terminal of a battery, negative ions are emitted that will be enter into the p region. So as here negative ions and already accumulated negative ions near to the junction before a before external voltage is applied, that will be a Diode takes place a recombination, since they have negative ions and negative ions near to the junction. So therefore weight near to the junction will goes increase, which was in case of forward bias. So deflection width is a more for a reverse. So definitely deflection width is a more. So means we have here a more field will be developed, more force will be developed, or more electrostatic field is developed. So we need here more potential. So it will give us more potential. And if you want to flow the carriers from holes to the carriers should be holes should be moved from the carriers to be combined with the holes and the electrons. We should break this barrier. Okay, so means to break this barrier, to break this layer, we need to apply external force V such that the it should be greater than this barrier potential. So means it can we can say that if we apply external voltage is less than its barrier potential, there will be no movement of electrons and the holes near to the junction. So therefore, there is no flow of there is no flow of a current, but there will be a small sort of a recombination due to the minority carrier, and which is with our naked eyes, which is seen at that is almost a zero. But if we zoom it back, it will look like this way, and this current is generally into micro ampere will be there. So means if we further extend this voltage, if we apply this potential very large, greater than barrier potential, then this barrier will be a break. If it is a break, then current will be flows. But for that case, what will be there? There will have the minority carriers will be there, and this minority. So means finally we can say that under the forward bias, the current will be flow once there a barrier potential break, which is a zero point 0.3 for germanium and zero point 0.7 for silicon. Whereas the reverse bias, this barrier potential is large, and in that case, once the barrier is a break, for that case again the current flow. Basic difference between these two, forward bias and reverse bias, is that in the forward bias, current is flow due to the majority carriers, and in the reverse bias, current is flow due to the minority carriers on their sides. So means now if we club these two characteristics, you will have the actual diode characteristic is a look like this way. So if you observe that before, if we consider that this curve for a silicon material, it's a barrier potential under the forward bias is a 0.7. So if you observe that before a forward our external voltage is a less than forward bias voltage, diode potential voltage, then it will be a small amount of a current, or initially zero current is flow, and then further slowly current is increased. Once the applied external potential is greater than barrier potential, then immediately current will be raised. And for a reverse bias region, this is a reverse bias region. For that situation, yes, more deflection will be or no movement of electrons, but small amount of a current will be flows. If we increase a further barrier potential, then the small amount of a current will flows due to the minority carrier. So finally, guys, you will have this one will be your actual diode characteristic. So this characteristic is divided into two parts. First is divided as a one part is a forward bias region where diode voltage should be greater than 0 and current should be greater than 0. Next is reverse bias region where diode potential is less than 0 and the current is also negative. And here it is a no bias point where you will have external voltage average voltage available at the diode is 0 and current flowing through that diode is also 0. Mostly guys remember that no bias point discussion we have. Now the important term associated with this PN junction diode. Okay, so we will concentrate from that one. So first one is a breakdown voltage. What is a breakdown voltage? Breakdown voltage is defined as maximum reverse voltage at which junction break down with sudden rise in reverse current. If we consider that diode is under reverse bias configuration and we want to flow the current, there should be a maximum reverse voltage we need to apply it. Next is that a knee voltage. If you concentrate for a forward bias characteristic of a diode, then up to the barrier potential, there is a small amount of a current is flows, and once the barrier potential, once the applied voltage is greater than barrier potential, current immediately raise. So means the point at which the current starts increasing rapidly is called as the new voltage. The forward voltage at which current through the junction starts increasing rapidly is called as a new voltage or cutting voltage or forward bias voltage or simply we call VF or in the most of the time we will simply call as a VD. Next is a maximum forward current. What is a maximum forward current? It is the highest instantaneous forward current that PN junction can conduct without damage to the junction. In case of a forward current exceed this rating, the junction will get destroyed due to the overheating. If we consider that guys here for a forward bias characteristic, then you will have the maximum current. If you consider this one, what is the maximum forward current? Here this one. How much? It can be for here we will have the maximum. Can we go for the beyond this one? Yeah, you can go for beyond this one. No issue about it. But if you go for the beyond this one, maximum current will be go flowing through a diode, and this will be a damaged diode, and so we need to take care of we have to limit this maximum current. So while and for to limit this for that purpose, we need to connect the external resistor for limiting the current flowing through a resistor. Sorry, current flowing through a diode circuit. Next, peak inverse voltage. It is a maximum reverse voltage that can be applied to the PN junction without a damage to the junction. If reverse voltage across the junction exceeds the inverse peak voltage, the junction may be destroyed. Yes, guys? Here, it is the maximum voltage you can apply. So here, if you show that, observe that it is a dotted line. If you go for the beyond that, barrier potential will break. Yeah, no issue about that. Barrier potential will break. Movement of electrons and the holes are, or movement of carriers are goes on. Current will be starts. But as the barrier potential is break, more current is flow, and this more current will be due to that junction will be more heated. And if it is junction is get more heated, that may be a destroy that component. So we have to take care of these parameters. So the if we apply how much amount of a maximum voltage we can apply to the diode is decided by the peak inverse voltage, and the peak inverse voltage is an important parameter while selecting the diode. And the lastly, maximum power rating. It is a maximum power that can be dissipated at the junction without any damage. So from this slide we can conclude that here we have the breakdown voltage, maximum reverse breakdown voltage, D voltage, where the current starts rapidly flowing, the maximum forward current. We should be limit the current flowing through current flowing through a diode. If maximum current is a flow, we need to connect here external resistor for a current limiting, and how much amount of how much amount of a reverse voltage we can apply, that is decided by the capacity of a diode, which is represented as a peak inverse voltage, and it's a dissipation. So now, what will be ideal diode? So the diode symbolically represented as like this way. So here it is a bar, this is a triangle, or it may be simply arrow. Its arrow indicates that the current will be a flows in this direction. So this side is we have a P material, and for this side is a N material, and so P side or a P type material is represented as anode, and the N type material is represented as a cathode. So here it is this one, and this diode symbol, this diode can be configured as forward bias and the reverse bias. To use the forward bias, what we will have? Positive terminal of a battery should be connected to the N side, should be connected to the anode, and negative terminal of a battery should be connected to the cathode. So as it is connected in this way, barrier potential near to the junction get reduced. Okay, barrier potential near to the junction get reduced. And for that case, what is the current flowing characteristic? Actual characteristic we have seen. If we say that here for this PN junction diode, if we say that here this diode is ideal, means there is a barrier potential is a zero. For that case, you have once the voltage is applied, the current will be immediately raised, and the voltage will be also there. So this is you have ideal characteristic of a diode. So, and what will happen for the reverse bias? Reverse bias, it will offer the maximum reverse voltage or maximum barrier near to the junction. So the current is flow actually like in this manner, guys. Yes, actually. But if you consider ideal, this current will be a zero. So means for ideal diode, for forward bias, current will be a immediately raised V is greater than 0 voltage, and the current under the reverse bias will be almost zero. So this will be a diode can be represented under forward bias and the reverse bias. For forward bias, the current will be immediately closed, and which is represented as simply a closed switch. And for reverse bias, current is never flow, it's a zero. Yeah, so it's an open switch. So means we can say that this diode is allow the current only in the forward bias configuration, never in the reverse bias configuration. So finally we can say this diode is a unidirectional device. So once the diode is a forward bias, then the current will be flow. So means finally you can say that this arrow indicates that current direction. Yeah. How it is connected in the circuit, according to that the current will be flows. That discussions we will have the subsequent lectures. So finally we can say that when the diode is ideal, it will be a for under forward bias it is a closed switch, and under the reverse bias it is a open switch. So you will have this characteristic course for the idea for the germanium material and the silicon material. Actual characteristics will be a linearly rising here. Forward current is linearly rising, and the reverse current is slowly increasing it with constant rate. So these are the ideal characteristics. Now, what are the current components associated in the PN junction diode that we need to observe? We know that if a diode is a, if we know that if a diode, we consider that no external applied voltage is there. Yes, there is a recombination near to the junction will be takes place. From electrons will be combined with the holes, and the holes will be accept, or it will be combining with the electrons. Yes. So as here P side and the N side are having their carriers. In the P side we have the majority carriers as well as the minority carriers as a holes and the electrons respectively. For the N side we have majority carriers are the electrons and the minority carriers are the holes are there. For if we consider that no bias is applied, then barrier potential is applied. Barrier potential is developed. Okay. Now, what will happen in the forward bias? If we consider that external voltage is applied to this PN junction diode by configuration positive terminal to the P side and the negative terminal to the N side, due to the forward bias, there exists a potential gradient in the P region and the N region. Now, the holes from holes from P and the electrons from N regions are injected into the N region and the P region respectively. The holes injected into the N region and the electrons injected into the P regions are the minority carriers once the barrier potential is reduced. What the barrier potentially developed across the junction indicator. So these minority carriers diffuse away from the junction exponentially with a distance as shown like this way. Exponentially diffuse at a junction here. Okay. Now let's we consider that their concentration falls steadily due to the recombination with the electrons and the holes respectively. Since the diffusion current due to the minority carriers is proportional to the concentration gradient, as in previous slides we have discussed, is current must be vary exponentially with the distance. Therefore, there are two majority carriers or diffusion carriers. Currents we will label these as I subscript EP of X and I H N of X. Here E stands for electrons in the P region and the H stands for electrons or H stands for holes in the N region. So guys, remember that here are the we are discussing here minority carriers in a associated the regions. In the P region, minority carriers are the electrons, and the N region, minority carriers are the holes. So let's the symbol of these represent the electrons current in the P region and the hole region, hole current in a N region respectively. So these, what will have? The electrons from P region and the holes from the N region. The holes will be moved from this direction to this direction and the electrons will be moved from left to right in the considering the minority carriers. So therefore, the current flowing through under this situation is due to the electrons, minority electrons, and due to the majority holes. So it will be thus the total current I at the junction at a distance, at a displacement distance x is given as like this way initially, guys. Okay, so the majority carriers, okay, holes, majority carriers or holes current in the P region is what? Is the majority carrier in the P region is holes, which is represented as this one. Similarly, for the majority carriers in the N region is represented as a I, E or I subscript E N will be there. And so for that, here we will have a majority current in the P region is given as I minus I subscript EP of X. Similarly here, I minus IHN of X respectively. So what will happen here as this one currents are flowing it? This these are the currents are developed. So it's a same that here minority carriers from the P region, which are the electrons, and the minority carriers from the N region are the holes. So definitely the concentration gradient will be changed. So what will be for the concentration gradient for the minority carriers in the P is exponentially increasing it. It's like this. Similarly, for the P region, minority carriers are what? Holes are there, and these minority carriers will be goes on. These minority carriers will be goes change the its potential gradient. Yeah, so it will be represented like this portion, this one, exponentially decaying. It's a so means due to the minority carriers, you will have the electron diffusion current will be potential gradient will be goes on changing it, increasing it, and here it is decreasing it. So means for a minority carrier, you will have the two combinations. These two. First is a electron diffusion current, and the second is a hole diffusion current. Now, if we consider that here a minority, next this P region can be also have majority carriers, and the N region also have the majority carriers. So what are there? Majority carriers are P region holes. Minority carriers, minority carriers are the electrons. Already we have discussed. We are discussing only the majority carriers. In the P region, we have the majority carriers are the holes, and in N region, we have the majority carriers are the electrons. So these majority carriers will be combined with electrons. It will be a holes will be a combined with electrons. So the concentration gradient, yeah, this majority carriers will be flow or combined with electrons because of a external force is applied. Once the barrier potential is greater than, once the applied potential is greater than barrier potential, the barrier will break, and these majority carriers will be combined with these majority carriers in the N region. So means definitely the concentration gradient of a majority carriers in the P region will be changing it. It will be decreasing it. At the same time, the concentration gradient in the N region is also changed, which is increasing it in the N region. So it's a represented graph like this way. So finally guys, we can say that the current component associated in the PN junction diode sorry, are current component associated with the PN junction diode are due to the majority carriers and the minority carriers. Before a barrier is to be takes place, minority carriers are present. Yes, that will be take a recombination and the current will be flows. So for that case, this here minority carriers in the P regions are the electrons will be combined with the holes. Yes, and the actual direction will be what? From a positive terminal, sorry, from a poles to the negative. The movement of electrons is here from a P side to the N side, and the whole movement is from a N side to the P side, considering the minority carriers, guys. Okay? So means you have the current direction due to the minority carrier is from a right to left due to the electrons, minority electrons, and the holes. Yes, again you will have a from a right to left. Okay, so similarly, once we applied barrier external barrier potential is external voltage is greater than barrier potential, this barrier will break. Once the barrier will break, majority carriers here is holes will be combined with electrons. Yes, or these electrons, majority carriers, electrons will be combined with holes. These electrons will move from N region to the P region. It's a movement of electrons. So what will be current movement? Current movement will be from a P side to the N side, or it will be left to right. Now, what will be movement of a holes? Majority, it's from a P side to the N side. Again, it's a left to right. So finally, we can say that here a majority current due to the majority carrier current will be flows, and current will be flows there due to the holes and the electrons. The holes current will be from a left to right, and current the electron current will be electron movement current will be from a left to right in the considering the majority carriers. In the minority carriers, what? Again, we will have here positive ions are the majority carriers. Sorry, positive ions are the minority carriers in the N region, and negative electrons are the minority carriers in the P region. Yes, and these electrons will be combined with here. The current direction will be from right to left. Yes, and the holes will be from again right to left. So means minority carriers, the current will be flows left to right, and the minority carriers, it will flows from right to left. So finally you will have these two currents are there, and this whole process is called as a free forming process. Next time, guys, we have how much time is left, guys? If it's a 4, okay. So we have enough time now. So guys, finally I conclude that here. Okay. So again, I am taking a slightly discussion about this one. So means, guys, what we can say, current component associated in a PN junction diodes are due to the one is a majority carrier, and second is due to the minority carriers. So majority carriers, current direction will be from left to right due to the holes and due to the electrons. And due to the minority carriers, the current direction will be from right to left, right to left due to the holes in the P region, and the electrons in the holes in the N region, and the electrons in the P region guys. So finally, here are four components associated in the PN junction diode, and the majority carriers two components, and the minority carriers two components are associated with the PN junction diode. And this one you will have this is a current component, direct current component in a forward bias PN junction. So guys, I request all of you, so you have to send your attendance in the format as a your provisional roll call number, serial number, sorry, your surname, and your first name, and ensure that before exiting that all of you have to subscribe for my channel, so you can get your today's lectures link on your WhatsApp group. Also, I am putting this link on our Moodle account also.